Hello dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Institute of Science, Department of Physics, Banaras Hindu University. Today we are going to talk on the module Introduction, Synthesis and Characterization of Graphene under the paper Nanoscience and Nanotechnology 2. After completing this module, the student will be able to learn about the miracle material graphene and the interesting history behind its discovery. They will also learn several synthesis techniques for obtaining such two-dimensional material. We will explain in detail chemical vapor deposition technique for the synthesis of large area graphene, and finally you will learn different characterization technique for confirmation of the presence of graphene. As you know, graphene is a monolayer of sp2 bonded carbon atoms packed into honeycomb crystal structure and can be viewed either as an individual atomic plane extracted from graphite or unrolled single-walled carbon nanotubes. This 2D graphene crystal exhibit many exciting properties like room temperature quantum Hall effect, long range ballistic transport at room temperature with around 10 times higher electron mobility than silicon, availability of charge carrier that behaves as massless relativistic quasi-particle like Dirac fermions, quantum confinement resulting in finite band gap, and Coulomb blockade effect in graphene nanoribbons or ultimate sensitivity of adsorption of individual gas molecules. This two-dimensional material, despite short history, has already established an area of exciting research for new physics and potential applications in electronics. To realize the above properties and applications of graphene, a consistent, reliable, simple and inexpensive method of growing high quality, uniform and continuous single layer and few layer graphene film is a prerequisite. Here I want to discuss crystal structure of graphene. Before going to graphene, I want to talk something about carbon. As you know, carbon is an element with symbol C and atomic number 6. It is a non-metallic and tetravalent, making 4 electrons available to form covalent bonds. Carbon is 15th most abundant element in the earth crust and the 4th most abundant element in the universe by mass after hydrogen, helium and oxygen. Carbon abundance, its unique diversity of organic compound and its unusual ability to form polymers at the temperature commonly encountered on Earth enables this element to serve as a common element of all known life. It is the second most abundant element in the human body by mass after oxygen. The atom of carbon can bond together in different ways, termed as allotrope of carbon. The best known allotropes are graphite and diamond. There are amorphous carbons also available. As I discussed about carbon, now let us talk about graphite. Size of a primitive unit cell of graphite depends on how the individual graphene layers is stacked to form a graphite crystal. Graphite is found in nature with various stacking arrangement, but here we will concentrate on most common and thermodynamically stable stacking, which is called Bernal stacking, AB type of stacking, which is shown in figure A. In Bernal stacking, the B atom in the second layer is directly above the A atom in the first layer, and then in the third layer there is A atom at this location, just as in the first layer. Graphene, which is the one layer of graphite, is another crystalline allotrope of carbon with two-dimensional properties. Its carbon atoms are densely packed in a regular atomic scale hexagonal pattern shown in figure B. Each atom has 4 bonds, one sigma bond with each of its 3 neighbors and one pi bond that is oriented out of plane. The atoms are about A0, which is equal to 1.42 angstrom apart. For graphene, a pristine unit cell can be defined as the smallest building block from which we can construct the graphene lattice. The primitive unit cell of graphene consists of 2 atoms due to its hexagonal structure, which we can label as A and B in figure B. Lattice vector can be defined as the vectors joining equivalent points in adjacent unit cell for monolayer graphene. Equation 1.1 gives these two-dimensional lattice vectors in terms of sp2 carbon-carbon bond length in graphene, which is A0. The accepted value for the bond length and the lattice constants are A0 is equal to 1.42 angstrom and A is equal to 2.466 angstrom. We can also see in equation 1.2 and define the reciprocal lattice vector B1 and B2 for graphene lattice using the relation A1 dot B1 is equal to 2 pi and A1 dot B2 is equal to 0. So this is all about crystal structure of graphene. I want to discuss electronic structure of graphene. Graphene zero band gap semiconductor, because of its conduction and valence band, meet at the Dirac point. The Dirac point are 6 locations in momentum space on the edge of the Brillouin zone, divided into 2 non-equivalent set of 3 points. The 2 sets are labeled as K and K dash in the figure. The set give graphene as a valid degeneracy of G mu is equal to 2. By contrast, for traditional semiconductor, the primary points of interest is generally gamma point, where momentum is 0. Electrons propagating through graphene's honeycomb lattice effectively lose their mass, producing quasi-particles that are described by 2D analog of Dirac equation rather than Schrodinger equation of spin half particles. This is a new feature in graphene system. The dispersion relation is given by the equation E equal to plus minus under root gamma square in bracket 1 plus 4 cos square kya by 2 plus 4 cos kya by 2 dot cos kx under root 3a by 2. When atoms are placed onto the graphene hexagonal lattice, the overlap between pi z orbital and the s or the px and py orbital is 0 by symmetry. The pz electrons forming the pi bands in graphene can be treated independently. Within this pi band approximation, using a conventional tight binding model, the dispersion relation, which is restricted to the first nearest neighbor interaction only, that produces energy of the electrons with wave vector k and as shown by the equation I have already discussed. With one pj electron per atom in this model, the valence band is fully occupied, while the conduction band is vacant. The two bands touch at the zone corner shown in figure C, where there is a zero density of state but no band gap. The graphene sheet thus display a semi-metallic zero band gap semiconductor character, although not if rolled into a carbon nanotube due to its curvature. 2 of 6 Dirac points are independent, while the rest are equivalent by symmetry. In the vicinity of k point, the energy depends linearly on the wave vector, similar to relativistic particle, which is a very special feature in graphene crystal. The synthesis of graphene means how one can synthesize graphene in the laboratory. To realize the application of graphene, a consistent, reliable, simple and inexpensive method of growing high quality, continuous and uniform single and few layer graphene films is a prerequisite. A knowledge of different synthesis method is necessary to understand why different graphene samples has exhibited property and to understand which synthesis method can produce suitable samples for a given experiment or application. The scalability and the cost of the different production method also varies widely. There are various synthesis approach which we can divide into two parts. One is top down and the second is bottom up approach. Let us first talk about top down approach. As the name suggested, the top down approach means from top to bottom, from larger to smaller. This approach is similar to making a statue made of stone. As in making of a statue, a bulk or a big piece of stone is taken. Similarly, in top-down approach, a bulk piece of material is taken and then curving it or cutting it down until desired shape is achieved. There are a few examples. The one very common example is mechanical exfoliation. The mechanical exfoliation technique has been used by two Nobel Prize winners, Geim and Novoselov, for making all their studies. The mechanical exfoliation or Scotch tape method was the method first used to isolate monolayer bilayer and few layer of graphene in 2004 by the Novoselov and Kine. The method exploits the weakness of the van der Waals bonding between the atomic layers of graphite flakes. A crystal of graphite is peeled apart many times with adhesive tape until at some location there was a flake of monolayer or bilayer achieved. However, the extremely small size of graphene samples ensure that this technique completely unsuitable for commercial production of graphene samples. Therefore, one should look for new synthesis route. Now let us talk about liquid phase exfoliation. This method involves immersing graphite flakes in a solvent and subjecting the suspension to ultrasound in order to simply shake the graphite apart into graphene flakes. It can produce far greater quantity of graphene than the mechanical exfoliated process. To begin, the liquid phase exfoliation process consists of subjecting a suspension of graphite flakes in a solvent to ultrasound. The solvent is chosen such that the energetics cost of exfoliating the graphite flakes into graphene flakes surrounded by solvent molecule is as small as possible. The liquid phase exfoliation process is important due to its scalability to produce large quantity of graphene for commercial use. However, it suffers from the crucial disadvantage that the monolayer graphene samples produced are mixed with a large quantity of few layer graphene and thin graphite samples. In addition, the sample quality is not as high as achieved by mechanical exfoliation process. Let us talk the second approach, which is the bottom-up approach. The aim is to produce large single crystal of graphene on substrate suitable for further study in a process scalable for commercial use. The mechanical and liquid phase exfoliation processes both fail to achieve this. The first bottom-up process developed by graphene synthesis was epitaxial growth, and the second, which is more widely used process, is chemical vapor deposition. Due to advantage of CVD over the other techniques, I want to discuss this technique in detail in next slide. The method of graphene growth most likely to prove suitable for commercial application in chemical vapor deposition on a transition metal substrate. A schematic has been shown here very clearly about this growth. The figure showing a schematic of liquid precursor based CVD synthesis setup. Here, the copper substrate has been used as a substrate, and the report of substrate selective growth of centimeter long, highly continuous single and few layer graphene film employing vacuum assisted chemical vapor deposition technique on polycrystalline copper foil using hexane as a novel liquid precursor been shown. The growth based on liquid precursor will certainly be an advantage over gas phase growth of methane or ethylene because most of the organic compounds and its derivatives are readily and cheaply found in liquid phase at room temperature. Moreover, handling and transportation for gas-based organic precursor like methane is always an issue, and we need a compressed cylinder for that. Another important issue is opening of band gap in graphene by chemical doping in carbon lattice. Liquid precursor based growth can help in realizing graphene doping because of nitrogen and boron containing organic solvents like pyridine or triethyl borane are inexpensive and easy to use, whereas the organic gases containing dopant atoms are rather uncommon. Doping can also be achieved by mixing a gas containing dopants atom with precursor gas, for example, methane and ammonia for nitrogen doping. However, this will also lead to inhomogeneities in gas pressure, flow rates, and doping over large areas. I want to discuss the transfer process of graphene. This is very much required because to study any application, especially electronic application, we have to put this graphene on silicon with silicon dioxide or dielectric substrate. Here I want to discuss how one can transfer graphene from copper to desired substrate. The most common procedure to transfer graphene is to cover the graphene sample in a thin layer of glass polymethylene methacrylate PMMA. The original substrate is then etched away, which is copper in our case. There are a number of reagents which can be etched away the substrate on which graphene is typically synthesized or exfoliated, leaving the graphene layer on PMMA intact, which is clearly visible in the figure. For instance, potassium hydroxide solution can etch away the silicon dioxide substrate in this process. The PMMA layer with graphene attached is then placed on the new substrate of your choice. For example, here we have taken on silicon dioxide, after which the PMMA layer is removed by dissolving it in acetone. The graphene is then left on the new substrate in the desired location. This procedure described schematically in this slide can be performed routinely on graphene sample produced by mechanical exfoliation method on silicon dioxide and by CVD on copper. Raman spectroscopy is a vibrational technique that is extremely sensitive to geometrical structure and binding within molecules. Even a small difference in a geometrical structure lead to significant differences in the observed Raman spectrum of a molecule. This sensitive and geometric structure is extremely useful for the study of the different allotropes of carbon like diamond, carbon nanotube, Buckminster fullerene, carbon nanoribbons, etc., where the different forms differ only in a relative position of their carbon atoms and the nature of their bonding to one another. Indeed, Raman has evolved into an indispensable tool in laboratories pursuing research into the nascent field of carbon nanomaterials. The Raman spectra of graphene and graphite, composed of millions of layers of graphene stacked together, are shown in figure 1. The spectra exhibit a relatively simple structural characterization by two principal bands designed as the G and 2D band Third band, the 2D band may be apparent in graphene when defects within the carbon lattice are present. These differences, although they appear subtle, supply very important information when scrutinized closely. There are differences in the band position and the band shape of the G and 2D bands, and the relative intensity of these bands are also significantly different. Clearly, these Raman spectra demonstrate the ability to differentiate between single graphene and graphite. However, the utility of Raman lies in the ability to differentiate single, double, triple layer of graphene. In other words, Raman is capable of determining layer thickness at atomic layer resolution. For graphene, layered thicknesses of less than 4 layers, for example, at the thicknesses that are of interest to the present field of graphene research. Let us now take a closer look at the vibrational band of graphene and how analyzing these bands can give insight into the thickness of graphene sample. The G band and D band is a sharp band that appears around 15.87 centimeter inverse in the spectrum of graphene. The band is an in-plane vibrational mode involving the sp2 hybridized carbon atom that comprises the graphene sheet. The G band position is highly sensitive to the number of layers present in the sample. This G band is also known as graphic band and is one method for determining layer thicknesses and is based upon the observed position of this band for a particular sample. The D band is known as disorder band or the defect band. It represents a ring breathing mode from sp2 carbon rings. Although to be active, the ring must be adjacent to the graphene edge or a defect. The band is typically very weak in graphite and typically weak in high quality graphene as well. If the D band is significant, it means that there are a lot of defects in the material. The intensity of D band is directly proportional to the level of defect in the sample. The 2D band is the final band that will be discussed here. The 2D band is the second order of the D band, sometimes referred to as an overtone of D band. It is the result of two phonon lattice vibration process. But unlike the D band, it does not need to be activated by proximity to a defect. As a result, the 2D band is always a strong band in graphene even when there is no D band present, and it does not represent defects. This band is also used to determine graphene layer thickness. In contrast to G band position method, the 2D band method depends not only on band position but also on band shape. I want to discuss the characterization of graphene using atomic force microscope. This microscope is a new technique to discuss the topography, and the height profile of the sample. AFM analysis also shown by the film are highly continuous and uniform in nature, visible in the figure. A large number of wrinkles were also observed on these films. This wrinkle formation occurs because of the thermal stress developed during the cooling of the substrate after the growth, as there is a wide difference in the thermal expansion coefficient of copper and graphene. I want to discuss the characterization of graphene using transmission electron microscopy. Transmission electron microscopy can be applied for fast thickness characterization of suspended graphene flakes. The folded edge of graphene like flakes provides a clear TEM signature of number of layers, which is clearly visible in the figure. We can see that in figure 1 we have one contrast, however in second we have a 2, 3 and many layers. The spacing between these layers is 0.335 nanometer. So my dear student, let us now summarize what you have learned in this module. Graphene is the first experimentally synthesized 2D material. Graphene shows the linear dispersion related to K point, which is very extraordinary thing in graphene band. Large area scalable synthesis of graphene can be achieved from chemical vapor deposition route, which is known as CVD route. In this CVD route, liquid precursor is more feasible than and less expensive than the gas precursor and easy to dope graphene by choosing suitable liquid precursor. Thank you.